So welcome everybody to this after lunch workshop on a topic that has to do with evolution, but it's not a biological topic. I'm not a biologist. I actually have a PhD in astrophysics, and I can already tell you this has nothing to do with astrophysics. So this is just my background. What I'm going to present here today is actually what I learned on my daily job. I'm currently a consultant at IBM in Germany, and I work a lot in the space of logistics. And in that area, there are a lot of complex questions, complex problems that need to be solved. And in the course of those problems and those solutions that I have developed and that I offer to clients, I come across a lot with evolutionary algorithms, mathematical evolutionary algorithms. And I'm doing this already for quite a long time. And there is an interesting question you can ask. Is there somehow these evolutionary algorithms, what are they exactly? How do they work? How well do they work? And can you somehow compare them to biological evolution or not? So this is the background of my talk. That means that I'm going to explain about those mathematical algorithms, how they work, give some examples of those, and then also make this comparison to biology. Now, if you are not a mathematician, you can still stay in the room, no problem at all. I will hardly show any formula, because this is about understanding how it works. And I'm not going to show you the depth and the details of programming on how to do that. That is not a target. So I hope that at the end you will have a feeling about these type of things, about, I would say, the amazing power of mathematics, but also about the limitations of it. So when I look at the overview of my talk, I will give a brief introduction to mathematical optimization. And this may be the hardest part. So if you are still awake after that first part, you will also stay awake for the rest of the talk. Then I talk about those evolutionary algorithms. What are they and how do they work? And then probably the nicest part for those that are really interested in nice pictures, we have very interesting examples of those, where this works and how that works. And then after having shown those examples, I'm going to kind of step back a little bit and say, what did we learn from that? And how can we compare that to biology? And what are the conclusions that I personally make out of that? So let's start with mathematical optimization. Mathematical optimization is talking about how do I find a solution for a certain problem. And most of the time this is find a maximum for something or find a minimum for something. And these problems can be either continuous or discrete. So in order to make that difference clear, I will give you an example for both. I'll start with an example that probably all of us, no matter what we did after that, have learned at school. I have a simple equation here, a function, and the question in school is, please find the minimum of that function. Now if I draw it graphically, I can see where it is. But the question is, can I also calculate it? Yes, of course I can calculate it, where the minimum is. If you have this function, that is a very simple thing to do, if you remember. If you don't do that in your daily work, you probably will still remember. It means that if you want to find the minimum, you have to differentiate that function. So you make the differentiation. It says 4 times x minus 40 must be 0. The solution for that is when x equals 10. And then I feed that back into the equation, and I say, well, the value when x is 10 is 50. And let's see, here you go. When x is 10, you have the value of 50. So this is a very simple mathematical problem that can also very easily be solved. Now you can imagine I'm not working 20 years on this problem, and that took a little bit less. A discrete optimization problem has a complete different character. So here is a question. I have a number of points on a surface, and the question is, find the shortest path that actually connects these points, all of them. Now you see that in this case it looks rather nice, so I think nobody needs to do any calculations here. and everybody can see, well, I just connect them like a circle, more or less, and then that's certainly the shortest path in this case. Yet, we have to be aware that this problem is a real different problem. First of all, there is only a number of solutions that I can take. So there is also a limited number of ways I can connect these points. And this number is, you can calculate, if you have the number of points, you can calculate how many different ways you can connect those. And in this case, the method would be, I don't know how to calculate this, so I'm simply trying all the combinations, and then I simply measure all the distances, and then I say, okay, this gives the shortest distance, this is my solution. So in this case, does anybody has a clue how many different passes there are here? So the number of different passes, if you would not see it visually where the optimum is, like in this case, is quite a lot. I have only 8 points, but there is 2,500 possibilities to connect those points. And in this case, 2,500, the computer can do that quite rapidly, so you would still be able to find the solution exact by simply telling the computer, try all of them and tell me which is the shortest one. That would work. So the method in this case is simply try all and find the optimum. Now this problem will come back a few times in this talk because it's a very good example of how mathematical optimization works. And also when this problem gets larger, it's getting really very difficult to find the optimum. And this is called the traveling salesman problem. You probably can imagine why, even if you have not heard that name. So there is a traveling salesman, and he needs to visit a number of clients in different cities. And of course, he wants to talk to the clients and not stay on the road all the time. So he needs the shortest path before he gets home in the evening. That's where this comes from. So we have seen there are continuous problems. And they have actually, you can say, the solutions in this continuous problem are very close to each other. So it's a compact solution space, you can say. And there are in an infinite number of solutions, but only one is the minimum. Whereas in the discrete optimization, I have a finite number of solutions. And these solutions can be very jumpy in the sense that two solutions that have almost the same lengths can look very different. So let's look at this situation here. I've taken the same pictures. On the left-hand side, for the continuous problem, solutions that are close to the optimum are also close together. On the discrete optimization problem, if I would add one point in the middle, it suddenly is not so clear anymore where the optimum is. Because from somewhere, from the boundary, I have to get into the middle to visit that city as well. So, for instance, I could compare these two solutions. It's not so easy to say which one of those is the best solution. And they look very different, but they may be the two nearest solutions. One is the optimum, and the other one is very close to it, but it looks different. So that's the, let's say, problem with discrete optimization problems, that the solutions can be very different and still have a very good value in terms of the shortest path in this case. So that we need to keep separate and apart. Now, if those problems, those discrete optimizations problems get larger, so imagine I have not 8 cities, but I have 765 cities or something like that. You can imagine that is really an amazing amount of possibilities that are existing. And then it's no longer possible to have an exact solution. I need something like an approximate solution. I need to find a way to get close to that optimum, even if I do not find it exactly. Now, the examples that we have seen so far are both exact. We found exactly the optimum. But for discrete optimization problems, there is a whole, let's say, mathematical discipline called operation research that looks at how to solve those discrete optimization problems. And they occur in a lot of different situations. And some of those you can solve exactly. There are certain methods for that. You may have heard of linear or quadratic programming, mixed integer programming. So these are techniques that are used to solve certain types of those discrete optimization problems. And they are still exact, and today computers are very fast, so there are quite large and complex problems that can be solved exactly today, very nicely. But I'm not going to talk about those. I'm going to talk about a very specific class that actually cannot be solved exactly anymore, where we need to approach the solution with trial and error methods. That means that I'm going to talk about approximation algorithms for these discrete optimization problems. And these are actually, in many cases, the only way of finding something which is close to the optimum, because I have no chance to find the exact optimum anymore. Okay. And certain of those discrete optimization problems are called NP-complete. I'm not going to explain the mathematical details behind it, but it is very easy to understand the principle. If you make that problem a bit larger, actually the number of possible solutions explodes. And here is an example again of this traveling salesman problem. We have already seen the case where we have 8 points, then we have 2,500 possibilities. If I only go to 10 points, I already have 100 times more possibilities, so almost 200,000. If I go to 20 points, I can't read the number anymore. And if I go to 30 points, it somehow fits on my screen, but, well, you can tell me what the number is, I can't read it. At least you see that this is really large. And real problems are typically even much larger. Which means that here, this enumeration type of thing, let's say, okay, let's try all and I pick the best, is no longer working. So I need really an approximation. I need to do something to get close to that solution, even if I don't know exactly where it is. Now there are, in the approximation algorithms, we still need to discriminate between what we call deterministic and stochastic algorithms. What's the difference? In a deterministic algorithm, it's like I construct a rule for finding an optimum, or for finding something that is close to the optimum. So I give like a rule how to generate a solution, and I follow that rule, and I get something which looks, let's say, more or less good. There are a lot of research is on construction algorithms for these type of problems, and they sometimes work very good, and sometimes they don't. So I have one example here. For that traveling salesman problem, one very known construction algorithm is, okay, I have a number of cities, not 8 anymore, I have 45 or something like that. They are randomly distributed in my area, so I can't see where the solution is anymore. I'm simply starting somewhere, and I look, where is the nearest point that I have not visited yet? Well, I have not visited any of those, so I can simply take the nearest city. Okay, now I'll connect these two. Now from this point, I'm going to look again. What is the nearest one that I did not visit? And so on. And this way, I walk through all the cities, and you probably can imagine what happens. In the beginning, that solution looks very nice, because you still have a large freedom of choosing a city which is very close. The only problem is, at the end, there may be 3 cities left that you did not visit, and then you have to like jump through the space to reach the final ones that you did not visit yet, and then actually you have a bad solution at the end. And this is a typical problem for these constructive or deterministic algorithms. They have some applications where they work good, but many applications where they do not work so good. And this is different from the type of what we call stochastic algorithms, heuristics that actually are not, let's say, fixing themselves to a certain solution, but trying to change the solution in total and find a good solution. Now, I here make my first remark and my link to biology. In microevolution, so life is adapting itself to its environment, we have a similar problem. We have many genes in the body that actually can be changed, can be merged, can be recombined to create new individuals. But there is no possibility to try all of the possibilities to find the optimum. And still it's observed in microevolution that actually life is able to fit itself to, let's say, existing environments and also to new environments. So this is where somehow a relation is that you can keep in the back of your mind. I'll come back to that later in a little bit more detail. So let's for the moment stay with those mathematical algorithms. And now we go to a very specific type of algorithms that we call evolutionary algorithms. Those are the ones that actually have an approximation way of working. So I'll try to approximate a solution. And most of the time they are used for discrete optimization problems. There are also other cases, but we stick to those ones. And there are different flavors of those. So evolutionary algorithms is like a whole set of different algorithms that people have developed and used for different situations. But there are some things that they have all in common, no matter how they are called. One is they have a way of generating new solutions out of existing solutions by making small changes. And you can imagine these small changes are called mutations. So I take a solution, I make a small change, and then I'm going to compare. I have more than one solution, so which is the best one? And then I have a certain way of choosing a good solution, which means that I need to be able to evaluate those solutions, say which is good, which is bad, and how do I decide which one to keep and which one not to keep. And this is only one step in the process. After I've done that once, I repeat it again, I repeat it again, I repeat it again. I keep repeating that until I have a very good solution. At least that's what I hope, when I did everything right. What's also in common in all those algorithms, randomness plays an important role in generating the mutations and also sometimes in how to select the good solution. So randomness plays an important role, and here you see again a link back to biology. Which individual actually crosses with which individual in nature, of course, often is a random process. Who meets whom? Yeah? Therefore, there is again here a link that we need to keep in the back of our minds. Now, there are some examples given here. There is a whole set of evolutionary algorithms that are called genetic algorithms. And this is most of the time quite complex algorithms. Here the idea is really to look at how biology is supposed to do evolution and take all these learnings and say, I'm going to make an algorithm that does exactly that. So in the genetic algorithms, you have things like, I have a population, I have recombination in there, I have inheritance, I have crossover, and all these type of things that you know from biology are then taken into this algorithm and trying to generate a solution. Now, there is also a set of solutions or algorithms that are much simpler, but they do have a similar, let's say, I would say, power of optimization and are easier to explain. And I will stick to those in my talk here. There is a set that is called simulated annealing, Cray-Deluge algorithm, threshold accepting algorithm. And those are very similar algorithms, and I'm going to explain one of those in more detail, and the others are very similar to those. So let's then have a look. What is the idea behind those algorithms? And we are talking here about what we call a threshold accepting algorithm. There is a reason why I've chosen this algorithm, and the reason is very simple. All of the programs that I've made for evolutionary algorithms are working with this technique, and they all work very good. So what you do is, you say, since I have no clue where the optimum of that solution is, I can also start with something that works. So a random solution. It is still a solution. So in the traveling sales problem, that would mean it's a thing that connects all the points. Every point is reached exactly once, none is reached twice, and none is not reached at all. And I end where I started, so it's a closed path. But that's all I say. It's a valid solution, but it's very likely not the optimum because it's simply a random connection of all of those points. I start with a solution like that. And in that solution, I'm then going to make small changes. Typical changes, okay, there is a part of that path is like crossed like this, and I simply change that path for the connecting points and make it like this. So I make only a very small change in that path, And then I'm looking, is this better or is it worse? If it is better, so if my new solution is better than the previous one, I say, perfect, I found a better solution. Yes, I take that one. And then I make my next step based on that one. It also can be that by the small change that I make, the solution gets worse. So in this case, the path becomes longer. And now it becomes interesting. Because if I would say, if it gets worse, I don't take that, then I may have a problem at the end. What happens if you only accept improvement is that you may get stuck in what we call a local optimum. So to give a better idea of how that works, let's for a moment assume you get a task of finding the highest mountain in the region of Wisla here. Okay? The only problem is you can't see. You don't know where it is. If you would be able to simply see it, we do not need a complex algorithm. So the way we do it is actually you get blinded and you walk around around Wisla. And you walk around and say, okay, it's going hill up. Ah, perfect, it's going hill up. I continue in that direction. And then you suddenly say, oh, I'm going hill down. No, that's not good. So you turn in another direction until you go up again. So you're always trying to going hill up. Now, if there is only one mountain and all the rest is flat, that would work perfectly. You would find the maximum without even seeing anything. You only feel, as long as I'm going hill up, I continue. And otherwise I go in another direction to find hill up. That works. But if the surface is not really having only one mountain, it has several mountains, and also it has very low mountains, if you only go hill up, you will simply stop on the first hill. That's it. You won't come away from that anymore. In other words, that means that these algorithms must not only allow for improvement, they also must allow for getting worse. On the other hand, if you say, well, then it doesn't matter, you can go up and down, it doesn't matter, you finally find it, I can tell you, you will never get there. So that means that you need something what we call an acceptance rule, a rule that says exactly when do you accept the solution, even if it becomes worse. And this is very important for those algorithms. That's why they are called threshold accepting algorithms. There is a threshold of how the solution can get worse before I say I don't want that solution anymore. Well, and that's actually a thing that you repeat all the time. And in a computer, you can sometimes do that very fast and many times. So you can have many, many different small changes and do this all the time. And at the end, you come up with a solution that works good. Wow. And the interesting thing is, while describing this technique here, I did not describe the problem. I only took the traveling sales problem as an example in my mind to explain it a little bit, but it never says here, I'm talking about the traveling salesman problem. That means that these type of techniques can be used very general for all types of optimization problems, as long as you obey these rules and work like that. And we also see later in the examples that there are actually very good examples for that. Now, there was one point I mentioned on the previous slide, that actually those algorithms are called cooling algorithms, and I probably have to explain that. So this threshold is called also often something like a temperature. And this threshold, so the way how you accept it and how you not accept the solution, is actually during the optimization you lower that one. So you make it smaller and smaller and smaller, and only at the end you only say I take only improvements. This is like, I first do not know where the biggest mountain is, but when I'm almost on the top of that biggest mountain, at the end I can say I only improve, and then I can simply go hill up and find the highest point there. And that's why these systems are called cooling, because this threshold is lowered during the optimization. Okay, let's look at some examples. I see most eyes open. That's very good, because then you had the heaviest part already behind you now. So the first one, indeed, is this traveling salesman problem, because that's the easiest one to understand how this works. So what we indeed do, I already explained it a little bit, we start with a random solution that every point is visited once, and you have a valid solution, but it's not a good solution. And now I start changing that solution. But before I start doing that, I also have to find an initial value of that threshold. So saying, what is the rate of, let's say, acceptance for solutions that get worse than the one that I have now? And here's already a trick that you can see. I say you need to take that threshold such that roughly, in the beginning, roughly 80% of the mutations in total are accepted. Where does that come from? Okay. Well, there's a lot of learning experience behind those algorithms, how they work good and how they do not work good. Okay. So there's nobody saying that this should be like that. But by working with those algorithms, you find that this is a good value to start with. Okay. So, and then you start this repeating, and as a mutation, I have only one possible mutation that I use all the time, and that's exactly the one that I mentioned before. I have two connections that I cross, or two cross connections that I take out of each other. It's the only change I make. Now imagine if you have, let's say, 500 points connected, and you only change the connection between two pairs of points. That means that the length of the whole path that you have only makes a change for those points. And all the remaining path is the same. This is very nice. Why is that? Because you can very rapidly calculate the difference between the old and the new solution. You do not have to calculate the whole path again. You only calculate the difference. That's why this mutation is used, because it calculates very fast. And then you repeat that, and during that repetition, you then lower this value of the threshold. So in the beginning, you have about 80% acceptance. In the end, you have then really zero acceptance. And then you hope you have a good solution. Now, I tried this. There is a nice video, if you wanted to see that. You will, at the end, be able to have this presentation. It will be distributed among the, I think, for all participants of the ELF. It will be available. And I could not run it from here. There was something blocked. I don't know what it is. So at home it worked. And then this is nicely shown as a video, but I also have some pictures on how that is. There is a very famous traveling salesman problem, and this is not really a traveling salesman. It's actually a print board where there is 442 holes to be drilled. And the drilling machine actually can move Euclidean distances, which means it goes from one point to the other. It simply moves like a straight line. So you can calculate what the distance is that the drilling machine is actually, let's say, driving to dig all the holes. And there is 442. This is a standard TSP problem. It has become something like a benchmark for algorithms. If somebody thinks, I have now a very good algorithm, it's much better than all the others before, he may first try it on that one. And then, because there's a lot of literature on it, and a lot of comparison, and then he can say, well, my algorithm is now 2% faster than the algorithm so far, and so on. So this is a very famous problem. And the L2 norm is exactly that. It moves on straight lines from point to point. And the target here is very clear again. It's just minimize the total distance drilling all the holes. Now, what you can see here, that these holes are not really randomly distributed. They have a certain structure. This is one of the nice problems. It had many points, but there is also an exact solution known for this one because of the nice structure. So you can, if you have a very complex algorithm and IDs, you can use that known structure to find an exact solution for this one. But that's not what we are doing. We are using this random process. I first show you one solution. This is not a solution that is random, and it's definitely also not an optimal solution. This was the solution that actually the manufacturer of those drilling machines had built into his drilling machine. Because they had a very simple algorithm, and you say you walk in the x direction, and the first point you find, you go there. And this is, and if you don't have any points more, then you go down and start again, because this drilling machine needed to drill very different print boards. Okay, and they could not put an algorithm or a path for every single board, so they had this simple algorithm, and it is definitely not a good algorithm, as you can see here. So let's forget about that one. But what is important, this has a total distance in a certain unity, be it millimeter or whatever it is, of 22,000. So this, let's say, was the original one. And now I say that this traveling salesman logic starts with a random solution. Okay, here is a random solution. It looks very nice. Okay, it looks like chaos. It is not chaos, because every point is visited exactly once. It's a closed path. It starts at the beginning, it ends at the beginning. This drilling machine would be able to drill like this, and at the end all holes would be drilled. Perfect. The only problem is it has a length of 78,000. And I get often asked when I talk about these things also with clients, can't you at least start with a smarter solution so you get faster to your optimum? For instance, like this initial solution, even if it's not good, it's much shorter. I don't do that. In those algorithms, it's best to really leave everything open in the beginning and let that algorithm find something and not put your intelligence into the solution because it may be different at the end. And then you are already fixing something that probably should not be fixed. So that's why we start really with a random solution. Now we let this technique run, and after a while, this is not the optimum yet, after a while you see that most of those very long links are already cleared up. So it already has found, let's say, major improvements in this path. We now have a length of 6,500, but you can still see probably that there are some areas, for instance, like the area here, where you say, well, I personally would have been able to find a better solution there if I just look at the solution. So this is certainly not the optimum yet. That means that we are not ready yet, but that's also the case here. So this was just a snapshot during the optimization. By the way, a very interesting thing, these algorithms allow to view the optimization at work. Those operation research exact algorithms like linear programming and so on, they are like a black box, okay? You just put something in, and at the end, if you're lucky, you get an optimal solution. If you're unlucky, after 4.5 hours of calculation, it says, sorry, can't find the solution, okay? So this one, at least you can see what's going on if you make those intermediate shots. So this is a solution that we find with this algorithm. It has a total length of 5150. And if you visually inspect it, you will not find areas, at least not easy, where you would say, oh, I see that I can't improve it any further. However, there are improvement capabilities because the known optimum has 5080. So you can see we are, let's say, 1% away from that optimum, which for practical application is most of the time very good. You see, this one was a doctor's thesis, okay? This one takes 25 seconds. Okay, 25 seconds against a doctor's thesis. In practical application is most of the time acceptable. And the main reason why this is acceptable is that the data that you work on most of the time have larger errors than the difference between those solutions. The only issue is, if I did not know that this is the optimum, do I have any idea whether this is close to the optimum or not? And that is very often is that an issue. So in this case, by visually looking at it, you say, well, I don't see any improvement anymore, so it's certainly quite close. But there are often problems where it's very difficult to say how close you are to the optimum. So that's also something that you need to take to keep in your mind. Okay, let's look at a few other examples. This is an example from production in a so-called flow shop. A flow shop no wait situation. Let me explain what it is. You have a certain product that needs to be produced in several steps on several machines. So you have, let's say, raw material going in at the beginning, you have production steps, and at the end you have a final product. And this actually, we have 50 orders here, and those are the colored things that you see. Every order is a separate color. And it starts on one machine, on the first machine. When it's done on the first machine, it goes to the second machine, to the third machine, and so on. And every time it's finished on one machine, it immediately continues on the next machine. And at the end, it's finished. So this is one order going through all machines. And this is why, why it's called a no wait. It's a flow shop, so the order of the machines is fixed, and no wait means once it's started, it must immediately continue on the next machine. There is no possibility to keep the intermediate result for a while. Now, these orders have different production times on different machines. So there are orders that actually take longer on machine 1, and other orders take longer on machine 2, and so on. So if I have now all my orders, and I know how long will they take on each of those machines, I now need to put those in such an order that the total time of putting them through all the machines is minimized, so that the machines are freed up as soon as possible. And actually, when I came to IBM in 1991, this was the first thing that I programmed at that time. And I heard also for the first time about these things, so I was really amazed about what my colleagues were telling me. Is this really working? Wow, I didn't expect that. So I programmed this, and also for me it was like, wow, this is really working. Okay, so I used these threshold accepting algorithms, and you see they are nicely put together. And actually the total time is shortened quite drastically compared to this, let's say, random solution I had in the beginning. So this is really working interestingly. Interestingly enough, there was a friend of mine. He was working at the University of Cologne in Germany. And he, in his PhD, was actually looking at this problem. And he was looking at deterministic, constructive solutions for that. So he had a lot of papers and a lot of formulae and ideas on how to construct good solutions for that one. And I started talking to him about that, and I said, well, I just learned in my company that there's a different way of doing this. I'm going to try that, and let's see and compare that. And he saw this, and he said, oh, why did you do that? Right, my doctor sees us here. You get solutions faster than I do. So this is a very powerful way of finding optimal solutions. Now here's another example, complete different, but also in production environment. I have seen 3 products in the beginning, and the easiest way of thinking of this is of colors. It actually was a different thing, but the way we present it to make it anonymous compared to what it was originally is simply we talk about colors. So we start with 3 pre-products or half-ready products, and we call them simply colors. And we have end products, and they are like a mixture of those 3 colors. So it's like color mixing problem. And this problem is now more complicated because I have different machines. Those machines have capacities, so I cannot produce more than a certain amount per day. When I change the product on one machine to another product, I have to set up the machine again. And you can imagine that this depends on the product that you change to. So if it is colors, you can imagine that if you change from a dark color to a light color, the machine has to be cleaned much more intense than if you do it the other way around. So all these type of information goes in. So this is becoming a quite complex problem. And then also you have certain just-in-time requirements. Things should not be ready too early and not too late, and so on and so on. And therefore, the challenge here, or the target that you want to reach, you want to minimize the total cost. So for changing the machines, and that things do not get too late, and so on. And also take into account the machine capacities. And all of that is then put in such a model. And once you have modeled that, that's actually quite a little bit of work. Then you use this type of algorithm. You let it run, and finally find a solution like that, which looks very nice. You see a very nice capacity, so the machines are used up. That's the size of the bars. You also see that the number of changes on the product from one machine to another, on one machine, the change of a product is not so often anymore. And this actually gives a very good solution compared to the previous one, which was a random solution. The interesting thing was, in this environment, the company, before they start using this, they were working with the rule sets. So they have made a lot of rules, like you are not allowed to change this product to that product on that machine because it takes too long. Or, well, there were more of that kind. I don't remember them all now. Most of those actually can be taken out as rules because this system will automatically find them. For instance, this number of how many changes do you have of the product on one machine, the system automatically recognizes that because it costs something, and it tries to minimize the cost, so it avoids it. So this is really very powerful. A problem that I've worked on many years, and with many different projects at clients, is what we call distribution planning, in sense of find the optimal number of locations of warehouses and where they should be, and how the clients should be served from those warehouses. So distribution network optimization. This is a case from the US. I worked a lot in Europe as well, as you can imagine. And this was the original situation at that client. They had many warehouses, and with many warehouses you would say, well, then it's easy to serve all your clients. But if you have many warehouses, it's difficult to keep all the products in the right warehouses. And as a result, they were doing a lot of cross transportation, because a client, let's say on the West Coast, needs a product, but that warehouse on the West Coast did not have it, so it had to come from the East, and they were transporting it all the way down there. And an optimal solution, or I have to say close to the optimum, was this: reduce the number of warehouses, and then it's easier to get the right product in those warehouses, and it's easier to align the clients to those warehouses. And this is all using all the same technique. You see a complete different application, and all of them use those evolutionary algorithms. This is another one here on the right-hand side. The number of locations of warehouses in Germany was reduced from 10 to 6, and some of them were staying where they are, and some of them were moved in different regions. And there was a quite substantial cost savings by doing that. Actually, this was my first project that I did. It was for my own company. And so the internal savings were calculated. They were quite high. And then I was able to sell it to other clients as well. Okay, there are more examples, but not all examples are so nicely visual. So I took only the ones that you can visualize the solution. So what we see here, you can say at the first glance, this looks impressive. You say, this is a stupid algorithm. It just tries something, and at the end it finds an optimal solution. That's perfect. So how can that work? It's in a surprisingly good results. And one of the developers of these threshold algorithms, he was my boss at a company in the beginning, at least for the first number of years. He was very proud presenting this, and he said, look, here we see evolution at work. This is how evolution works, and we have demonstrated that it works. And already at that early times, I had debates with him, and I said, well, I think there is more about evolution than just this. What you see at work is microevolution, not macroevolution. And he was looking, what's that? What's the difference? Okay, so I had to explain him what the difference was, and I come to that in a minute. But you see how people actually make conclusions out of those algorithms and say, oh, exactly, that's working. Randomness is enough to create beautiful things. Okay, if these algorithms are not stupid, okay, then of course there must be some intelligence here. So where is the intelligence here? And so we look a little bit more on that. And we also can say the other way around. Well, if there is if it is intelligent, what then would be a real stupid solution? So can it be more stupid than the ones that I have shown? Yes, it can. And let's have a look at that. So the intelligence, actually, in those algorithms is first of all, in the proper choice of the mutations. And second, in the way you control this process of optimization. So let's first look at the choice of the mutations. If I say I start with a valid solution, and I transform that valid solution in another valid solution, I have to think myself first, what kind of changes then do I need to make that happen? And if I use a method of generating mutations, how can I be sure that by using those mutations, I catch the whole solution space? And you can imagine like a solution space, like a high-dimensional cube, where all the possible solutions are in, depending on which things I change. And by making those small changes, I must be able to get everywhere in this solution space, because I don't know where the optimum is. So if I have a mutation that does not cover all the possibilities, I probably won't find the optimum, because I miss it. So that means that there is an intelligence needed to find the right mutations. In the case of this traveling salesman problem, I told you I use one mutation, but also there it's not trivial to prove that this mutation is enough to find a solution. It probably could be that it is not enough and you need more than one solution, one mutation. And in the more complex problems that you have seen, actually more than one mutation is defined. Sometimes up to 5 or 6 different type of changes I need to implement, really program into that system to make a good solution at the end. So I also need to make sure that I do not actually ruin my solution. So the mutations must be in somehow, let's say, not too bad. So that should not actually make my solution dead, that it does not survive anymore. I'll come to that a little bit later also in what is a bad mutation as an example, but keep it in mind, those mutations have certain characteristics that make it work. The other thing is that cooling process. I already gave you a hint, like in the beginning you should take your, calculate your threshold such that you have roughly 80% acceptance. So how is that done? What you do in those algorithms, in the beginning, you just make a lot of mutations without acceptance or not acceptance, you just calculate them. So let's say you have 10,000 different passes you've calculated, and then you say, okay, how much do they vary? Okay, and then I know where I need to put that level of acceptance to make sure that roughly 80% of those actually run through and 20% are not running through. So I can then exactly calculate that initial value and start from there. The other thing is, during this cooling process, this is not linearly going down. So it may be that if you lower your temperature, that you come at a range where actually you have to stop cooling for a while because there is so many things happening in that area, where in other areas nothing is happening, you can easily cool down further. So this whole cooling process is not like simply go down and you have it, but it's like you have to control this process. And what we implemented is a so-called PID control mechanism that actually feeds back the result into itself in order to learn how to cool the process. And this is quite an intelligent instrument to make it work. The interesting thing is this threshold accepting algorithm has been debated in literature quite often. And when it is debated, people typically compare it to other algorithms. So they compare it to simulated annealing, to their own algorithm, to a genetic type algorithm. And what we often found in those literature, that this algorithm actually was getting bad rating. So like the threshold accepting is not working in our case. And we were working on those things, and we know exactly what was going wrong. They did not have a good control mechanism. They were simply cooling down rapidly, and then you have a bad solution. It was not a surprise for us, but it was difficult to actually fight against. So these type of things are very important, and otherwise this is not working. Now, if you have more complex things, so let's for a moment think of this situation where I do the color mixing. Okay, you need several mutations, not more than one, and the mutations sometimes can be quite complex. So it's not just simply take one product, put it on another machine, but probably take one order with different products and put it completely on another day or something like that. So these type of more complex mutations turn out then to be more effective, which probably is not a very big surprise, but then they of course must be programmed and implemented, which is then a lot of effort. And you really have to avoid disruptive mutations, things that actually make your solution so bad that you can't revive them anymore. So the solution is actually then really corrupted, it's broken, and you can forget about ever finding a good solution. Another issue is if you have more than one mutation, some of those mutations may make a big change in the result, and others may make a small change in the result. And if you simply use both together, then the big ones will actually change everything you did in the small ones. So then you have to look at how often do I allow a big mutation compared to a small mutation. For instance, you may say the small mutation is running 100 times more often than the big mutation to get this effect away. So here again you see somebody thinking about it, how can I improve it, using that effect and then get a better solution. Okay. So as soon as you do not do these things properly, you won't find good solutions, and you may not even find a solution at all at the end if you have done things wrong. So let's go back to that very simple example of the traveling sales problem. What could you do wrong? Now imagine I would have a mutation that says delete the connection between 2 points. And another mutation, add a connection between 2 points. Actually, I would then leave my solution space. That means I would generate solutions that are not valid anymore, because certain points would not be visited, other points would be visited more than once. And if you start doing that, you will never find a good solution anymore. It's simply a way. I mean, we have been trying those things. Adding these type of mutations, you end up with complete chaos at the end. It will not work. But you also can have wrong control, and that's what I already said. If some of the ones that implemented these type of things with those algorithms found a bad solution because they did not have proper control mechanisms. That means that you need to be very careful with what you are doing there. I am already coming down to a conclusion from this, and in the conclusion, I will now try to relate this back to biology. And therefore, I have made this comparison overview. And my conclusion is the following. The optimization using evolutionary algorithms needs a very careful design. It needs accurate implementation, and it needs a fine-tuned control. If you don't do that properly, it will not work. And I'm not talking about programming errors. Those programs are quite complex. If you make a programming error, the program will not run at all, okay? You have programmed everything properly, but still you have taken the wrong mutations or the wrong control, and you already get away from optimum and you can't find it anymore. And therefore, I think in this respect, evolutionary algorithms can be compared to what we observe as microevolution, where actually living individuals over many generations are capable of adapting themselves to certain changed environmental situations, and in the following respects. So the first thing is that I observe from the evolutionary algorithm, the mutations make sure that one valid solution is transformed in another valid solution, be it better or worse, but it's a valid solution. For living individuals, that means that I have creatures and they generate similar creatures, okay? Very similar creatures, actually. In the evolutionary algorithms, those mutations must be chosen intelligently. I really have to think about it, what I'm doing. And by the way, I'm probably just jumping back a little bit to that one example with this optimization of distribution network. I have tried very different mutations here to find what is the best mutation with which this is working properly. And I have come up with one mutation which does the following. I take one warehouse randomly, that's where the randomness comes in. I move that warehouse to another location. Let's say I move this one over here. But then I have to do another thing. Because if I move this one over here, some of the clients that I'm serving now need to be allocated to another warehouse, because that's now closer. So that means move the warehouse, reallocate your clients such that, again, all the clients are reached from the nearest by warehouse, and that's one mutation. So it's a very complex mutation. It does a lot of things. But using that mutation, I found very good solutions. One of the alternatives I've been trying is work with a combination of mutations. One is simply move the warehouse, but do not reallocate your customers. The other mutation is take one client and move it from one warehouse to another. And this was a mixture of a small mutation, named just hanging one client to another warehouse, compared to a large mutation, move the whole warehouse with all its clients. And there I found all these difficulties, that actually the solutions was all the time running behind and lagging behind. Because I let this recombine or reallocate the client, I let it run very often, but then when the solution almost looked correct, I took one warehouse and placed it somewhere else, and I could start over again, okay? So that did not work really. So I was trying different mutation types, and they did not properly work. And therefore this is very important that those mutations actually are chosen very intelligently, and by choosing them intelligently, they guarantee that the solution remains valid. And this is actually what we see in biology going on. Mutations are not really random mutations, because we have a genetic pool of capabilities, and if two individuals actually come together, they have differences in the genes, and they are actually merged together to generate different variations, but both are living creatures. And the possibilities of changing those genes in the next generation are actually such that, again, you have an individual that lives. It does not die immediately. And the interesting thing is, there are also things like what we call random mutations, that certainly something goes wrong in the genes, and some mutation that probably was not foreseen, it was not there, it was not capable, then comes and actually changes something. Now these mutations are known to be destructive in almost all of the cases. There are certain cases where a destruction actually leads to an improvement in the sense of environment. The best situation I have in mind always is like ice bears in the North Pole, okay? There is a mutation changing the color, and actually they are missing the gene that actually causes the color, so they are white. And white in a polar environment is actually good for those animals because they survive with a white skin, okay? But that does not mean that white was a new color that did not exist before. It came into existence because the color gene was broken, okay? So destructive sometimes can be advantage. But what we do not really see, at least to me it's not known, that we see that really new structures, complete new things that were not there before come into existence by mutations that you use. And it is exactly the same in those evolutionary algorithms. If I allow for mutations that leave my solution space that I have defined, I will find chaos at the end and not a complete new way of visiting my clients in a traveling salesman problem, for instance. Okay? So wrong mutations destroy the solutions. Wrong mutations degenerate life. There is, I think it was a book, I think it's only available in Dutch, degeneration it's called, where all of these things are very in detail studied, that really describes what the changes in life actually cause, not better structures, but only degeneration. Which means that if we talk about these algorithms and we say, well, this is just a random algorithm, it tries something and then it finds a good solution, perfect, we need to be very careful because the randomness in those algorithms is purely restricted to the selection of the next mutation. The next couple of points, for instance, in the traveling salesman problem that I'm going to reconnect, that's a random choice. But everything else is really very fine-tuned, designed to make it happen. And I would state here that it is the same for microevolution. Randomness is restricted to the selection of the individuals that actually combine. And everything else is beautifully designed in such a way that it, at the end, improves for the environment. If the environment changes, it improves that the survival of those individuals is actually getting better. I think this is more or less the end of my talk. I have put in a number of references here. So some of the things I explained with those threshold accepting algorithms and with simulated annealing, there are good papers on that if you are interested to look further and learn something there. You see there is also a paper of myself about a problem that I did not describe in detail because it's visually not so interesting. But it's one of the biggest applications that I ever wrote on this. And I can tell you in a few words what it is doing. I'm working in the automotive business, and we are looking here at spare parts in warehouses all over the world for a big automotive client. And they have many, many different warehouses, and they have the question, which parts do I put in which warehouses? Which levels do they have in terms of to catch random fluctuations and still be available? How often should I replenish them? Do I allow for something like a rush order to be placed if the part is not available, or is it too expensive, and so on? So a lot of things, and this has been implemented using these algorithms, and this automotive manufacturer is using these techniques every week to calculate for all the worldwide warehouses every week what is the optimal levels of inventory for spare parts in those warehouses, and that works perfectly. So a big application, but as I said, not visually, not very attractive, but a lot of money involved for the client.